I'll lead up to this, okay? All right, so the quick idea is this. If we start off with something like linear momentum operator minus IH partial with respect to x, all right, and we operate P on psi, all right. The question is do we get h bar k times psi? And the answer is yes. We've done that, all right. Everybody agree? As we pull out the linear momentum, h bar. And we talked about this being, and so the answer is yes, indeed. So yes. And we have an eigenvalue problem. All right. How about if we did this? How about if we went p bar? Well, let's do this. Let's let psi go to apples times psi. All right, no kidding. Apples times psi. All right, if I now go p times psi prime, let me make that prime, what happens? I still get minus I h bar partial with respect to x of apples times psi. Now this would be the unprimed psi. All right, and what is that going to equal? So what does this operator do to this thing in front of my wave function? Apples is it a variable, a function of x? No, it's some constant, right? So what's going to happen? This operator is essentially going to move through here, right, using the product rule, and then operate on this. And when it operates on this, what does it pull out?
HK.
H bar k, right? So this is going to come out to equal h bar k all times apples times psi, or p times psi prime equals h bar k times psi prime. Okay, so what was the effect of putting this constant in front of my wave function?
Nothing.
Okay, nothing. In terms of what we call the observables of these operators, the eigenvalues of these eigenoperators, of these operators. All right? So the stuff in front didn't have to do anything to do with the expectation value of the momentum, right? Everybody agree? Okay, so the way you want to think about it is the wave function carries things for the operators that are operating on it, like position and momentum and angular momentum and energy. All right? But the stuff in front of the wave function doesn't have anything to do with that. Right? When I act on, when I take a prototypical thing, how about 7 times e to the I kx and 9 times e to the I kx? If I operate p bar on this thing, and I operate p bar on this thing, what do I get?
So I'm going to take out the h bar k. H bar k.
You get h bar k times 7 e to the I kx. And here you get h bar k times 9 e to the I kx. Right? Okay, so what happened here is, so in both all these cases, we have p times psi equals h bar k times psi. All right, so the operator is essentially pulling stuff out of this, out of, the wave function itself. And the part in front of it has to do with the normalization, which is just the probability. Okay, watch. Let's let over here, here's what we need. We need the total probability to add up to 1. So let's generalize this. Minus infinity to plus infinity. And what I'm going to do is I'm going to let psi go to n times psi. I'm just going to let it be called n, some constant in front of it times psi. Right? And let's let it be, in this case, n times e to the I kx minus omega t. Because this is our prototypical plane traveling wave solution. Right? Okay, so what I want over here is this needs to be psi star psi dx. Alright, and that has to equal 1. So we have the integral from minus infinity to plus infinity of n star, complex conjugate of n, and then I need a complex conjugate of this. What's the complex conjugate of that?
E to the I kx plus omega t?
Nope.
No, it's e to the I negative kx.
Nope.
Or just kx minus omega t.
Nope. Where's the I? Right there, right? There's a positive here.
Yeah.
So make it
Negative I.
That's it. Minus I kx minus omega t times, now it's just n times e to the I kx minus omega t dx. Has to equal 1. Hold on one second. Yeah. Okay. Okay, I've gone off a path that's bad here. So let me not use this example, guys. I'm sorry. I'm in bad shape today. I apologize. I have to stop here. I have to stop at that point and merely rewrite this without that specific example. All right, because that does not work. Because plane waves are not normalizable. I made a big mistake. So over here I have the integral from minus infinity to plus infinity of n star psi star psi dx, and then up, and then I need an n. Okay. Now this is a constant, so a constant is real. All right. So n star is going to equal n. So what I'm left with here is that n squared times the integral from minus infinity to plus infinity of psi star psi dx has to equal 1.
Can divide both sides by the
Yep, so you divide both sides, and when you divide both sides by the integral, what you get is n is going to equal 1 over the square root of the integral from minus infinity to plus infinity of psi star psi dx. Okay, so what did that force n to do? And why is it called n? N is called the normalization constant.
To make the final value something Real?
Okay, not just real, but to make it equal to
1.
What it does is it forces this whole thing where we identify psi star psi as the probability, all right, the probability density. Because it forces the whole probability to integrate from minus infinity to plus infinity to give you 1. All right.
So the reason, like, that right here, like, it lists the normalization equation as the absolute value squared.
Yeah.
But then we use the star because with the complex conjugate.
Because the wave function itself could be complex.
Okay.
Right. So over here it has to be complex.
So in this case, we're going to be using an imaginary number, so that's why like I is in the equation. That's why we use the complex.
Yes. Yes. So if you have a complex number, you need to know the magnitude of it. You have to use the complex conjugate. Okay. All right. So now this gets to Dale's question, and it also, I won't go into it, but I use plane waves. And plane waves, look, I'll tell you. I said I'm going to use our prototypical example, plane waves. And plane waves are the prototypical answer. But plane waves are not normalizable. And not normalizable means they can't represent something physically real. So even though plane waves are the solution to Schrodinger's equation and they're a solution to Maxwell's equation, they're not physically real. Alright? That's a problem. But what we're doing is that plane waves are an infinite basis set. Which means that real solutions can be built as linear combinations of the plane waves. Alright, so I got myself into a bit of a trap there because I went to use a real solution, but indeed the real solutions are not normalizable.
It's not normalizable because they go on forever, right?
So very specifically, let's talk about what normalizable means is. Normalizable means that for this to be true, right, that the integral from minus infinity to plus infinity of psi star psi dx has to be finite.
Can you repeat that?
This is the definition normalizable. Okay, that it's finite. Okay, watch. I guess I can do it this way. And then Dale will get to this question over there where you can start to see it. Alright?
So in the other case, it was not finite, it was infinite?
Yeah, it was infinite. So you can't normalize plane waves. So if you put in plane waves here, it becomes infinite. It's not a finite.
Just think about it. You're trying to integrate something that keeps on going
Right.
forever in other directions.
So I was trying to come off with an example off the cuff of my head, and I shouldn't have. It was the prototypical correct answer, but it was the absolute worst example because it's the case that doesn't help us. All right, so watch this. If I have a wave function, as long as it, for example, let's do this. Let's say I have a wave function minus infinity to plus infinity of psi star psi dx equals 42. Right? You know, because that's the number in that book. What's that book?
Hitchhiker's.
The Hitchhiker's Guide. All right? So look, it's 42. It's finite. So that means it's normalizable. Okay? Now watch what happens when it means it's normalizable. Maybe this is all done very good. Okay? Let's let psi go to some normalization constant. This would be called the normalization constant times psi. And this is going to pull it together. All right, so now I'm seeing this is going to pull it together nicely. Okay, so watch what happens. I am now going to do this as minus the integral from minus infinity to plus infinity of n star psi star times n times psi dx. All right?